So with that said, I definitely want to save as much time as possible for the NASA team to go ahead and tell us about their story. So funded by the NASA's HQ Group for Transformation and Innovation, our next group of presenters were tasked to test Azure's AI and ML capabilities. Led by Johnson Space Center's OCIO, Martin Garcia, use cases from centers across NASA have been brought to the table to test their impact on mission projects. They're in varying stages of testing and run a spectrum from cognitive search to full machine learning. To introduce his team and projects, I'll hand you over to Martin.
Hey everybody, how's it going? We pull up the slides, Patrick.
Should be here. One moment.
Excellent. Okay, hello everybody. My name is Martin Garcia. I'm the JC OCIO for Artificial Intelligence and Machine Learning. Next slide. And this is the agenda that we're going to be covering today. We're going to do a brief overview of the digital transformation Microsoft Azure AIML project, and we're going to do a deep dive into the onboarded projects, some of them. Next, please. So this is a brief overview. So essentially, my mission is to enable all NASA data scientists and engineers easy access to state-of-the-art AIML technology. So this technology is relatively new to NASA as far as Microsoft Azure. So we had to go through a whole process just to build it out. One of the first things we had to do was make sure that it followed current NASA policies and security checks, which it did. It checked off really well. Then we wanted to make sure we secured an environment for our AIML users, because we have NASA data. We wanted to make sure it was secure. So we did that, and once everything was good to go, the next step was basically start working. So one of the first things we wanted to do was to start initial training and adoption support. So we onboarded multiple AIML projects, specifically from the Flight Operations Directorate. Can you go back one slide, please? Specifically from the Flight Operations Directorate and the Engineering Directorate. And currently, we're only allowed public and moderate data classification onto this platform. This wasn't just me. This is a whole team of people that helped build this out. The cloud within NASA. So the Cloud Service Provisioning Office, they were a huge help, and the EMCC, the MAX team, ICAM, the Microsoft Federal was amazing, and the Information Resources Directorate really provided a lot of support. Next slide, please. So if you see here, this is the available AIML analytics services. This is just one screenshot of it, and as you can see, there's a lot. Next slide. So what we want to do is kind of focus more on the cognitive service capabilities, specifically vision, speech, language, knowledge, and search. Next slide. And these are the NASA mission use cases for FY21. The first three is what we're going to be covering today, and the last three are natural language processing projects that we won't cover today, but I can briefly talk about it. The first one is the Crew Comet Database Sentiment Analysis, and that's essentially trying to determine the astronauts' emotional tone when they that they carry, whether that's positive, negative, or neutral. The second one is Voice Assistant for electronic crew procedures, and it's exactly that. It's an astronaut doing a certain crew procedures, but having a voice assistant to help them get through it step by step. And the last one there is the real-time mission voice, and that essentially is being able to get telemetry data from the mission, specifically for voice, and trying to deploy that into a model, containerize it, and put it on an on-premise data center for additional testing and evaluation. And that's all currently in work. Next slide. So word got around of what we've been working on at NASA, and it got to HPE. So when they found out we had some machine learning models that we've been doing, we're in X amount of iterations, they said, hey, would you like to try to put that machine learning model on the International Space Station? And of course we said yes. Right? It's called Spaceborne 2. It's a HPE Edge cluster that's currently on the International Space Station, and it was deployed to provide artificial intelligence processing. So our mission and what we want to do when we get up there is essentially test the machine learning models on the ISS using the HPE Edge cluster, and of course we're going to have HPE and Microsoft data science support And we're going to be running these containerized models in submarine mode, which basically means like disconnected from the internet, essentially. When we get to the moon or we get to Mars, there's going to be a lot of times where we're going to be without internet, and we need this machine learning model to be able to function in a submarine mode. Next slide. Okay, so let's get down to it. These are some of the projects that we're going on. The first one here is the machine learning for EVA glove inspections, and that's it's run by Jordan Lindsey and John Sokowski. Take it away, guys.
All right, thanks, Martin. Appreciate that. So I'd just like to say a big thanks to John Swiatkowski. I'll be the presenter for the presentation this afternoon, but had a lot of help from John, so thanks for that. I appreciate it. Next slide, please. So what is the problem and what are we taking a look at here? So what we're trying to focus on from an EVA perspective is being able to expedite the process of being able to use machine learning to speed up the process of giving a go or no-go recommendation for the spacesuit gloves. So why is that a problem? As you can imagine, being in a low Earth orbit where the International Space Station is located, the crew use and abuse the gloves quite often because their hands are their primary mode of transportation around the International Space Station when we're doing an EVA or a spacewalk. So the gloves see a lot of abuse, wear, and tear. And what we're focused on for our first initial part here of using machine learning is being able to give an expedited recommendation of go or no go. Currently, that process can take up to 5 days. So we're trying to expedite that any way that we can. And just like Martin was alluding to, as we move out to lunar and onto Mars, the frequency at which EVAs happen are going to increase, and the environment is going to play a big role in the wear and tear that we see on those gloves. Being able to give the crew the autonomy that they need to be able to make a go or no-go recommendation for gloves to continue to be used is going to be very important. So we're trying to utilize the International Space Station as a test bed for that. And the way that process works out now is during an EVA, there can be two types of inspections that happen. One is actually during the physical EVA itself, and this is performed by the crew. The crew approximately every 90 minutes will do a glove inspection. And for an example, you can take a look at these photos that we have here on the right. So that's going to happen about every 90 minutes after the crew do a major translation. Again, they're using their hands to get from work site to work site, or after they do a hand-intensive task dealing with various fluid or electrical connectors. We like to get a glove inspection to make sure gloves are okay and no damage has been occurred at that point. But the part that we're focused on for this project is that post-EVA glove analysis. So once the EVA is over, the crew has come back in. The crew will actually use a very specific camera and a setup to take photos, very similar to what you see here on the right. And those photos then are downlinked to the ground, where a ground team of experts will gather all those photos, somewhere between 20 and 40 photos per crew, and take a long, hard look, zooming in on photos, getting photos from various angles, trying to be able to take a look at any damage that may have occurred to those gloves. And then at the end of that, they come together as a team and make a recommendation if the gloves can be used or not for a subsequent EVA. Okay, next slide. So where are we with this? We tried to approach it from a two-phase problem, and we're currently in phase one, and thanks to Azure, we're already working on that. So what we've done is we've gathered approximately 3,000 photos that already existed in Imagery Online, which is a NASA-based photo repository. These images come from previous EVAs that were used to build, construct, and maintain the International Space Station. And we've taken those images and we've put them into Azure and tagged them accordingly, whether they're go or no go. And then we've also used additional tags to help identify different damage modalities that we might see on these gloves to help narrow down a prediction as to whether they're go or no go. And what we're currently working on is being able to position ourselves to work parallel with an upcoming EVA. Currently, that's scheduled in the March-April timeframe. Could be a little bit earlier, could be a little bit later. But what we're working with the team of experts on the ground with is being able to work in parallel and be able to give a recommendation to that team and see how close we are. Are we close to that same recommendation, or what are things that we can do to improve our model and algorithm? The second phase of that, which will be continued on after the using static images, is to move on to HD video. We currently have HD video capability with the spacesuits now. So we would like to investigate the idea of moving this from just static images over to video and being able to expedite that even faster, being able to potentially provide a real-time go or no-go recommendation. Okay, let's get into a few results. Next slide, please. All right, so what we're taking a look at here is just a comparison through various iterations. We've done about 9 iterations of our model so far, and utilizing a photo here from one of our test images is an actual glove used on the space station after an EVA. And what we've done here on the ground is we've circled the area of concern in red that's been done by us on the ground, not by Azure. And what we're highlighting is an area of concern that would deem this glove no-go. That is a hole that has been placed or punctured into the Vectran layer, and that is actually a cut resistance layer on the glove. So we know that the crew has come in contact with something that's very sharp somewhere during the EVA. And as you can see in iteration 1, we were using a binary tag system, go or no-go, based on the photos that we had. And incorrectly, it was identifying this as 99%, we're going to give you a go recommendation. It absolutely is not. And by iteration number 9, we can see the tables have turned. So we're up to about an 83% recommendation there, which is very good, a strong turn of events compared to iteration 1. So we're starting to see things come online, things like RTV wear. So just to make you kind of point that out here on this image, that light gray material that seems to be missing near the index of the, at the base of the index finger, that's considered RTV wear. So it's that material that's able to be removed during an EVA. That's fine. We see that fairly often, and it's kind of what it's there for, is it's the first layer of defense and that can be used on the glove. So that's acceptable, but we like to be able to identify those areas and see if there are any changes or recommendations that we would give based off of that. So it is starting to pick up on things like that. Okay, next slide. But not everything is great. It's not picking up on everything, obviously, so we still have some work to do on our side to help identify some issues. So what we're taking a look at specifically here is another glove, very similar in the damage modality to what we were seeing on the previous image. It's not circled, but you can see there near the index, base of the index finger, a blue, light blue area that is sticking out of the Vectran. Again, this is a hole in the Vectran, and this is a no-go situation. These gloves cannot be used again on the space station, so it's a hazard. When we ran this through our iteration number 8, again, it was picking up on something incorrectly and identifying this as a go condition of about 98%. It absolutely isn't. And by iteration 9, what we've been able to see is that turnaround. It's dropped the go recommendation quite substantially. Now it's saying about 38%. And it is most definitely picking up on the RTV wear condition that we were wanting to highlight as well. Part that's a little bit concerning to us still is the Vectran damage tag that is still low. It's approximately 2%. As you can see, between 8 and 9, it has increased, but the real concern here are 2 tags. One, it's a no-go condition, so we'd like to see that higher. And the second being identifying that Vectran damage, that it sees a problem with the Vectran in the image. So that would be another one that we'd like to see a little bit higher. Okay, next slide. So what are some things that we can help us figure this problem out? So what happened between iteration 8 and iteration 9? Things like explainable AI. So there are some different functions that are available on the Azure platform to help with the interpretability of the model. So we'd like to explore that a little bit more, maybe using computer vision and actually delving into the machine learning aspects of Azure to be able to help with that. Be able to increase those predictions on those various tags that we would like to see. And in this case, being able to most specifically pick up on the no-go portion of that. So that's where we would like to see things turn around. But we're very interested in using explainable AI to help with that. Okay, next slide. So just to kind of wrap this up here from our side real quick, overall, the glove project that we've done so far utilizing the custom vision, it is possible to identify a go, no-go condition. We've seen that. But we would like to continue working with our iterations. Are we overfitting the model? Are there problems that we're seeing? You know, part of the increased recommendation that we've seen was taking additional photos of what's called class 3 gloves. These are gloves that are utilized by crew when they're training in the neutral buoyancy laboratory. They see even tremendous amounts of wear and tear, what they can see there in the NBL compared to what you can actually see on orbit. So we'd like to replace those glove photos with photos of actual class 1, what is used on the International Space Station that may have seen some of that damage. So trying to be able to get some photos of those to be able to feed back into our model to help with that. Again, using that explainable AI portion of Azure would definitely be very helpful. And then to get back to the aiding in the crew autonomy portion of this is training at the edge. So being able to solve the problem of a constrained bandwidth like we would potentially see on the lunar surface, and then most definitely by the time we get out to Mars. And as Martin alluded to and was speaking to, the collaboration. So we've started a collaboration with HPE and Azure Space to run our latest model on the Spaceborne 2 computer. So we're in works for that and look forward to being able to test it out on the International Space Station. So that's all I have on my side. Thanks.
All right. Next slide, please. Good evening, everybody. My name is Nick Gambirasi, and I'm a machine learning and image analytics intern in NASA's Image Science and Analysis Group. And today I'll be taking you through how we've been using Azure for lunar dust detection and mitigation. Next slide, please. So as NASA prepares to take astronauts back to the moon for the first time since the 1970s, we have to re-explore the problem of lunar dust contamination on spacesuits. So as astronauts walk on the lunar surface, they collect more than trace amounts of lunar dust on their spacesuits. This is typically connected through standard movements like walking, and also you can collect large amounts through certain events such as falls. And the problem that this presents is that the smallness of the particles and the sharpness of the surfaces typically makes lunar dust very unsafe for astronauts. And it's not always easily detectable with human eyes. And the search for lunar dust, specifically those trace amounts, is very time consuming. So our solution to this problem that my group's been working on is an Azure-based object detection application for lunar dust mitigation. Now we've divided this project into 3 phases. The first phase is an experimental phase. Due to the price of the spacesuit fabric and the lack of availability of it, we chose to use a similar fabric called Nomex fabric. And since this, there's a lack of imagery of lunar dust on these types of fabrics, so we've generated and imaged 2,000 fabric samples on our own, and we've split it into training and test data sets. And we've used Azure Custom Vision to train both standard and compact models for online use when you have access to Azure, and then also for submarine use, as Martin alluded to earlier. We also used the Azure Custom Vision built-in metrics to evaluate these models, and used outside test sets to ensure that the models weren't overfitted. And then moving into phase 2, we started building an app that allows users to input live imagery through their laptop and perform predictions on those images using both the online and submarine models. And then finally, phase 3, which is where we're headed, is the expansion of the model to include the spacesuit fabric rather than just experimental fabrics. Next slide, please. Now, as we jump into the phase 1 results, this is all on experimental fabric, and we expect these results to transition over to the spacesuit fabric pretty well. In the initial iterations, we noticed that Azure really struggled to distinguish between like image noise shadows, or image noise which was represented as shadows from fabric wrinkles, and the dust contamination itself. So to combat this, we implemented the pre-processing framework, a bunch of image pre-processing to differentiate between the dust and the image noise so Azure can better recognize it. Working into the middle phase of iterations, in this phase, The models are trained against a small pool of processed images, and the results improved, but there were a lot of false positives, and then failures to detect are still common. And of course, we need to focus on removing as many of those as possible. And then moving into the final iterations of this phase, using data set augmentation, we're training against large pools of processed images, and we're seeing some very positive results here, high precision, high recall. On our test data sets, very limited numbers of false positives and failures to detect. So as the iterations continued, the model continued to improve. Next slide, please. Now, as we move into phase 2, the application, the functionality essentially works with 2 different types of Azure models. The Azure online models use prediction endpoints within Azure to perform the prediction on images. And then for the offline functionality, compact Azure models are exported and referenced in the application itself. The application itself works with a live camera feed from an HDMI input. And the user functionality, you can press the space bar and it'll capture that specific frame from the camera and perform the dust detection predictions on it. And then it'll send back the detected dust and where it is on the image. Next slide, please. So the conclusion we've established thus far, as we've moved through phases 1 and 2, is that the models built using Azure Custom Vision are successfully detecting lunar dust on the Nomex fabric. Of course, this is dependent on the image preprocessing, as I discussed briefly. The model needs this preprocessing step to distinguish between the image noise and the dust itself. And then as we move into phase 3, the future testing will determine our hypothesis, or will either sustain or refute our hypothesis that the models are as reliable for detecting the lunar dust on the spacesuit fabric itself. And as we move into phase 3, we will begin acquiring the new spacesuit fabric for imaging. We will build a permanent imaging environment for spacesuit fabric imaging, and then obviously we'll continue training and tuning the new fabric machine learning models. And we're also interested in exploring different ways to evaluate these models using Azure Computer Vision and Azure Machine Learning to explain or work with explainable artificial intelligence as well. And yeah, that's really all I have on my end. Thank you.
Cool, so I'll be taking over from here. I am with the Cruise State Cognitive Determination Project. That is me, Frank Delgado on this call, Paz Knight-Givon, and Kyle Nguyen. So we are going to be, we're looking at using biometric sensors for cognitive state classification. And what that really means is we're trying to monitor and predict off-nominal cognitive conditions expressed as a task saturation gradient that we're classifying based on physiological sensors. Basically, there's not a whole lot of work that's been done to understand regular stress-affected cognitive function. More so, the focus in terms of physiological sensors has been basic health and cognitive health overall. But we don't have a solid way to associate task-saturated conditions with these biometric sensors on the ISS, and it hasn't been expanded past basic health and cognitive health monitoring. So what we need to do is collect task-associated biometric data across workload gradients, and we do this with 2 different types of tests. The first test is shown up there in the upper left. It's a validated method for assessing task saturation on task performance and attentional blindness. It was developed by NASA Langley, and it's been validated and used multiple times in many other different studies to help assess that. We figured it would be a good ready-made solution to help put our participants in these different workload conditions. And aside from that, we have our flight simulator here. Now, this is a hold down from a methodology on a, originally when it was being adopted to the Air Force, we essentially have our participants perform different maneuvers that are labeled across this workload gradient as low, medium, high. And then also TLX subjective workload data is collected during that time after each of those tasks. And it's associated with that to help get our accurate labels. So we collect a whole suite of biometric sensor data. We cast the net as wide as we possibly can, with the obvious ones that are pointed to in the literature is associated with cognitive load, like our cardiac measures, heart rate variability. But we've also expanded into experimental sensors like FNIRS and plenty of EEG contacts that are integrated between the Muse commercial sensor and an actual EEG array in the VR environment. So what we hope to do is use that task-associated biometric data and classify it along a single dimension, which is our workload gradient of baseline, low, medium, and high workload. Now, these states aren't strictly defined in the literature, so the problem is a little bit esoteric in terms of assigning these labels that are validated to them. But that's why we rely on things like the MAP-B validated in the literature and our subjective workload rating. So the point of this chart is to help emphasize that and help show exactly what we're looking at. We're trying to identify patterns in the biometric sensor streams that are associated with the different workload gradients. This plot is repeated of the same kind of task. This is the same participant and the same suite of testing, but 3 different tasks, 3 different repeat measures, and those have been plotted here. And we're hopefully trying to gain a little bit of discrimination power out of that in terms of assessing cognitive load. So Azure has helped with this very much because what this requires is massive data sets of biometric sensor data. And there's advantages with doing it in a local environment, but there's also lots of advantages to doing this kind of work in a collaborative computing environment, on top of being able to access, the machine learning workstation itself. Those compute resources that are hosted on the cloud help handle this massive amount of data really well. So, in the old architecture that we were doing, offline away from Azure, we would get the sensor data out of the database, and a human would have to first off look at the raw data, validate it, plot it, and then also run serial Python scripts that reduce the data, add our features, and then also split it out into training and validation data. And then the person also starts the AML process inside of whatever environment we're using, our local environment. So now Azure has a lot of opportunities for improving this, and we've essentially adapted every single one of those serial scripts to an automated pipeline that we can just push this raw biometric sensor data into and have it start training on the other side. So moving through here, we have parallel applications for each of these different nodes in the pipeline that we were doing outside of it in Azure. We do AZ copy to an Azure blob account, and that moves into a featurization script, and then that takes care of scaling and resampling as well, using our using scikit-learn libraries and the things that we call inside of the Azure environment. And we end up with training and validation data that gets sent right to AutoML in Azure. So the actual training interface for this is a dream. It's really easy to see all of our experiments, and our central workstation for training allows us to look at the status of each one, assess the performance if we were to drill down a little bit further, but also just look at our overall session, because a large portion of this work comes from retraining on and experimenting with different subsets of data. So we quickly build out lots of different experiments. And here's a good visualization of that diagram that I showed earlier, the way it's actually expressed inside of Azure. We have each of our custom Python scripts that have been implemented inside of Azure, connected to each other, and you can actually see how each of those work or feed into each other. This is an example of one of those custom scripts. For example, this was our featurizer, which takes all of our raw data and calculates the features that have been identified in the literature as transformations that are appropriate for discriminating workload power or workload intensity. But Azure also lets us able to specify our logging and send all of those logs that we specify to a centralized location that we can review. This goes in hand with our explainable AI as well. Azure offers a pretty powerful tool set to get a good status on what the performance of these models that are being trained, how they're doing. So we have our regular outputs like our confusion matrix and our precision scores and the regular stuff that would be included in an ML platform. But we also have helpful features like this feature importance diagram, which for tabular machine learning is very helpful because we get to see the importance that each of our columns had on the actual overall training performance. And we also get to view and edit our hyperparameters from a centralized location, which is very cool and can be implemented in a pretty inconvenient way in some other platforms. So that's cool to see. This is an example of the types of visualizations, custom visualization scripts we want to implement inside of Azure. We've got, regular bar charting. We have a quantifiable significance testing in this chart, pairwise comparisons across the different workload gradients. But this is an example of where we want to move towards with Azure and adding an extra step into this process where we're able to do visualizations like this automatically as part of the pipeline. So we were able to move our workflow into Azure, and it handled the scale of the data that we were doing really well, and painted a path forward for continuing that workflow so that we can produce results quickly. On the actual training performance side, the only way that we can build our performance out with this type of model and this type of problem is to expand our patient cohort and collect as much data as possible. That's really how we get there. But this collaboration with Azure allows us to set up a very a convenient pipeline for processing and actually using that data for training. And that is all we have on our end.